Okay, I'd like to welcome everyone to our seminar and remind you, as you just heard, the meeting is being recorded. Our speaker today is Matthias Wink from the University of California, Los Angeles, speaking on new curvature conditions for the Bochner the Bochner technique.
Yeah, thank you very much for the kind introduction, and thanks to the organizers for giving me the opportunity to speak here. And yeah, so I'm going to talk about new curvature conditions for the Bochner technique, and everything that I say is based on joint work with Peter Petersen. All right, great, let's start. And first of all, I'd like to set the scene. So in the following, we'll always talk about a compact Riemannian manifold, n-dimensional. And let's say it's connected, and for simplicity, we can also assume it's oriented. Okay, so that's what we'll have the entire talk. So let's start with the classical Bochner technique. What do we do? Let's pick a one form omega, and we can apply the Laplace operator to it. Okay, so we consider the Hodge Laplacian first, dd star plus d star d. And the trick is we can write this also in terms of the connection Laplacian. Okay, the connection Laplacian is nabla star nabla omega, but we make a mistake, and the mistake is given by a curvature term. And if we have a one form, this curvature term is precisely given by the Ricci curvature evaluated on the vector field that corresponds to our form omega. Okay, so what can we do? Well, let's assume we have a harmonic form. That means we've got a form that sits in the kernel of the Hodge Laplacian. We can calculate the Laplacian of half norm omega squared. Okay. So we're going to get two terms. The first term is the norm of the covariant derivative of omega squared. And the other one is going to be minus the connection Laplacian of omega. And because we assumed we have a harmonic form, we can actually write this as the Ricci curvature evaluated on omega. Okay, so that's the observation that Bochner made. And so what do we get out of this? Well, let's suppose the Ricci curvature is non-negative. Okay, obviously the norm squared is non-negative always, so we know that the Laplacian of the norm omega squared is non-negative. Okay, now we're on our compact manifold, and the maximum principle will tell us, hold on, the norm omega squared actually has to be constant. So we get 0 on the left-hand side. And that also already implies that omega is parallel. Okay. And moreover, if we also know that we've got positive Ricci curvature, then evaluating omega on the Ricci curvature here shows that actually omega has to be 0. Okay, and then we can use Hodge theory and say, well, every cohomology class is represented by a harmonic form. And we've just seen if we've got positive Ricci curvature, then every harmonic one form has to vanish. And so the first Betti number of the drum cohomology has to vanish. And that's the basic idea of the Bochner technique. And this general strategy is also the strategy that we'll have in the remainder of the talk. But we want to talk about p-forms. Okay, so what happens for p-forms, not just for one forms? All right, we can write down the Bochner formula again. Okay, so we have the Hodge Laplacian, and we can write it in terms of the connection Laplacian. And again, we make a mistake, which is given by the curvature term. And because for one forms we saw it's really the Ricci curvature, it is also called reach of omega. But now we have a p form, And so Ricci omega is really a P-form. It's not the Ricci curvature anymore. So what is it actually? Well, to say what a P-form is, we have to evaluate it on P vectors. And what do we want to do? Okay, let's look at the expression here. We want to take the curvature tensor R of our Riemannian manifold and apply it to omega. Okay, so more precisely, we'll take a vector field, xi, and in the ith component, we'll plug in ej, which is an orthonormal basis of the tangent space that we're looking at. Okay, and then we want to sum over ej and go over xi through all the positions. Okay, do we have to remember this formula? No, that's not the one that's really helpful to understand this curvature term. And as we go along, we'll try to understand this curvature term better and give a new perspective on it. What we want to keep in mind is that it really depends on the entire curvature tensor. It's not just the Ricci curvature anymore. It's a complicated expression. Okay, so we have a Bochner formula. The curvature term is more complicated, but it's of the same type as before. And again, we can play the same trick as before. Let's suppose we have a harmonic form. Then we can compute the Laplacian of half the norm omega squared. Again, we get the norm of the covariant derivative of omega minus the connection Laplacian of omega. And because we have a harmonic form, we get the curvature term, and this is given by Ricci omega paired with omega itself. And so for one forms, this was precisely the Ricci curvature, and now it's a curvature term that depends on the entire curvature tensor. Great. And if we know that the curvature term is non-negative, then we can play the argument that we played before again. We can see that the Laplacian is non-negative, and hence we have a parallel form. And so the general strategy will still be the same. Great. Okay, so let's try to get a hold on this curvature term. And the basic observation that we start with is, okay, so we look at the curvature tensor and we see, okay, once we plug in xi and ej, we've plugged in two vector fields, and the symmetries of the curvature tensor tell us we're going to get a skew-symmetric endomorphism of the tangent bundle. Okay, and we can identify skew-symmetric maps with wedge 2. If we look at V wedge W, that's really a rotation in the plane spanned by V and W. That's the identification that we are using. And once we start thinking about wedge 2, the natural object to consider with regard to curvature is the curvature operator. So let's recall how the curvature operator was defined. Okay, we take the 0,4 tensor Rm, and we can evaluate it on x, y, z, and w. And due to the symmetries, if we look at x wedge y and z wedge w, we can define this way a curvature operator on wedge 2. And we also know that we can flip the first two with the last two arguments due to the symmetries, and that says the curvature operator is self-adjoint. Okay, and we can diagonalize any self-adjoint endomorphism. So what we're really interested is the eigenvalues of the curvature operator. Okay, so now once and for all for this talk, we want a fixed notation. Lambda 1 through lambda n choose 2. These are going to denote the eigenvalues of the curvature operator of our Riemannian manifold. And the C alphas, they're going to be an orthonormal eigenbasis of the curvature operator. Okay, and we've noted we can identify wedge 2 with skew-symmetric linear maps. And the following goes back to Poor in the 80s. And his idea was, okay, we have the curvature tensor here, which is a skew-symmetric endomorphism. And we can write it in terms of our eigenbasis of the curvature operator. And the remarkable observation that he made is this. He can calculate the term which appears in our Bochner formula. And namely, it depends on the eigenvalues of the curvature operator times C alpha on omega and the norm of this squared. So I have to explain what this means. We're looking here at the derivative of the regular representation. Okay, so if we've got a skew-symmetric map and omega, and we want to know what form this is. And we can apply C to each individual vector field, and we'll sum over all of those. And the derivative tells us we're also going to get a minus sign. Okay, so if we go back to our formula up here, there's the Ricci identity, which tells us if we want to apply the curvature operator, the curvature tensor to omega, that is the same as applying the curvature tensor to each individual argument and summing over up to a sign. So that formula down here really incorporates the same action up here. Great. And this proposition of Poor, that is really the starting point where we want to go. And Poor could recover some amazing theorems in the Bochner technique with this basic observation. And so I'd like to continue now with some historic context and main theorems. Okay, great. So what do we have? I've written down the formulas again that we've seen on the previous slides. And our idea is we look at the curvature term and we want to see it's non-negative. Then the Laplacian is non-negative, and we see that omega is parallel. Okay, and we can express the curvature term in this way that we've seen. It's the norm of C omega weighted by the eigenvalues of the curvature operator. Okay, so I'll reverse history slightly and look at the case when the lambda alphas are non-negative first. Okay, if all the lambda alphas are non-negative, then clearly the right-hand side here is non-negative, and we can run our argument and show that omega is parallel. And that's a result due to Gallo and Daniel Meyer from the mid-70s. If we have a manifold with non-negative curvature operator, then every harmonic one form is parallel. And we can do more, or we can say more, if we have positive curvature operator. That's due to Daniel Meyer. Okay, then we can again evaluate the curvature term on omega, and we see that C alpha omega has to be 0 for all alpha. And that is sufficient to actually show that omega is 0. And then we can use Hodge theory again and say every cohomology class is represented by a harmonic form. And we can deduce that all the Betti numbers vanish except for the trivial ones. So we're sitting on a homology sphere. Great. So that's the somewhat natural generalization of Bochner's result for 1 forms to P forms. And later on, Gallo developed the Bochner technique further to incorporate non-positive curvature. So what do we want to do? We want to have a bound on the curvature operator from below by a possibly negative constant. Okay, so let's pick kappa non-positive. And a lower bound on the curvature operator means that all our eigenvalues lambda alpha are bounded from below by kappa. Okay, so that's the natural curvature assumption. And we also need an upper diameter bound now, an upper diameter bound by D. And once we've got these two ingredients, then Gallot can show that he has got a bound on the Betti numbers. Namely, the pth Betti numbers bounded by n choose p times a constant, e to the c times square root minus kappa d squared p times n minus p. And what is interesting to observe here, if we plug in kappa is equal to 0, then this part here is 0. And one can also calculate the constant here explicitly in this case, and it does not blow up. So really, what we get is 0, so e to the 0 is 1, and we get the optimal bound on the Betti numbers and choose p. Optimal because for the torus, obviously, we get equality. Great. So these are the classical results from the Bochner technique that we aim to generalize further in this talk. And I would like to somewhat put these classical results into a more modern perspective, which brings us to Ricci flow and positive isotropic curvature. And in this regard, there's one more result that comes from the Bochner technique, which I would like to mention. It's this result here of Mikhaev and Wang. If we've got an even dimensional manifold with positive isotropic curvature, then they could show that the second Betti number vanishes. Okay, so they don't have a result for all the Betti numbers, but they can at least show that the second Betti number vanishes. And later on, I'll indicate somehow how we can prove this again with a slightly different technique. Great. So positive isotropic curvature is a curvature condition that really naturally comes up in Ricci flow, and it's much weaker than positive curvature operator. So let's put these results into context and recent results with Ricci flow. Okay, so here we are. The first main result is Bohm-Wilking's result, which is based on work of Hamilton and then generalizes also work of Chen. So what can they show? Okay, they can show that if a manifold has positive curvature operator, then it's diffeomorphic to a space form. More precisely, they can even show that if the first two eigenvalues sum up to something positive, so the manifold has two positive curvature operator, then they can run the Ricci flow on this manifold and it will evolve the metric into a metric of constant sectional curvature. Okay, so if the manifold is too positive, then lambda 1 can be negative, lambda 2 has to be positive, and all the other eigenvalues also have to be positive. But it's certainly a weaker condition. Great. And then based on Bohm-Wilking's work, Brentle and Shane proved the differential sphere theorem. And in this context, what they needed from Ricci flow was that if you have a manifold so that its product with the plane has positive isotropic curvature, then again, the Ricci flow evolves the metric into a metric of constant sectional curvature. And hence they get a diffeomorphism classification to a space form. And then Brentle actually generalized this further to pick 1, which means that M cross R has positive isotropic curvature. Great. So these are the results in Ricci flow theory that give us a diffeomorphism classification with a space form, and in particular, they imply the vanishing results that we've seen previously with the Bochner technique. And the Ricci flow is even stronger. It gives us a diffeomorphism classification, which the Bochner technique doesn't allow for. And we've seen Gallot's result with a lower bound on the curvature operator with negative curvature. And there's one result which I'd also like to mention in Ricci flow, which has a lower bound on the curvature operator, which is negative. And it's this recent result of Bamler-Cabezas, Rivas, and Burkhardt-Wilking. So what does it say? We fix a dimension, we fix an upper diameter bound, and we fix a lower volume bound. Then we can find an epsilon, so that if our curvature operator is bounded from below by minus epsilon, then we can find a metric of non-negative curvature operator on our manifold, and we get the rigidity theorems that we've seen before. Okay, and it's noteworthy that within Ricci flow techniques, as of now, we can't get rid of the lower volume bound. Whereas in comparison, Gallot's result did not assume a lower volume bound, it only needed an upper diameter bound and the curvature condition. Great. So we've set the scene. Let's look at the main theorem of this talk. And yeah, this is recent work with Peter Petersen. So let's recall where we are. We're on a compact Riemannian manifold. Let's say it's connected, and we can also, for simplicity, assume it's oriented. We can always go to the orientation double cover to get rid of orientation, but for simplicity, let's also say it's oriented. Okay. Then we can use Poincare duality, and we can restrict ourselves up to half the dimension. Okay, so let's pick a P form, which is a 1 form up to an n/2 form. Let's pick a lower bound on the curvature operator as we did it before, and an upper diameter bound. Okay, so Gallot's result said if lambda1 is bounded from below by kappa, we get a bound on the Betti numbers. Okay, so our result says we can do better. We can look at the average of the first n minus p eigenvalues of the curvature operator. Once we've got a lower bound, kappa, then we can recover the bound on the Betti numbers that we've seen in Gallot's theorem. Okay, so Gallot had a lower bound on the entire curvature operator. With Ricci flow techniques, we still had a lower bound on the curvature operator. And we now say, actually, we can write a condition down which grows in dimension, or rather gets weaker as we grow in dimension. Great, and then again, we get the optimal upper bound for the Betti numbers if kappa is equal to 0 and choose P. And moreover, this is also something that Gallot has seen already. If the product kappa d squared is bigger than a certain epsilon that depends on the dimension, then already we get the optimal bound on the Betti numbers. Okay, so that's the result if we've got non-positive curvature. What about the corresponding rigidity and vanishing results? Yes, we could do this too. So if the sum over the first n minus p eigenvalues is non-negative, then our curvature term will be non-negative and omega is parallel. And I will say a few words about the proofs a little later. And we also have the vanishing result. If the sum over the first n minus p eigenvalues is positive, then omega is 0. And we can use Hodge theory again to show that the Betti numbers vanish. And the natural question is, well, how many eigenvalues do we have to sum up to see that actually we're all the Betti numbers except for the trivial ones vanish? And the answer is, well, we have to go up to half the dimension. And this is the next corollary. So if we sum up lambda 1 up to lambda n/2, take the ceiling function of this, if this number is positive, then actually we can show that we're sitting on a homology sphere. Okay, and again, for Ricci flow, results, we needed lambda 1 plus lambda 2. And we can get a condition which grows linearly in the dimension. So let's compare the result that we have with the previous results. So one important feature in the Ricci flow results is that non-negative curvature operator or two non-negative curvature operator, non-negative isotropic curvature, pick 1, pick 2, they're all preserved by the Ricci flow. So their proof really starts with the observation that they have a curvature condition which is invariant under the Ricci flow. The curvature condition that we've written down, they're typically not Ricci flow invariant. So I say typically because we can arrange for our sum to be lambda 1 plus lambda 2 again, and then it would be preserved. But Bohm-Wilking already observed that if we look at lambda 1 plus lambda 2 plus lambda 3, this is not preserved by the Ricci flow. And one can similarly see that lambda 1 plus lambda n minus p is typically not preserved by the Ricci flow. Okay, so we've got a key difference already to the previous results. But still, you might ask, is this weaker than the results that we've seen coming from Ricci flow? Or are we just looking at a curvature condition which is already implied by something else? And there's a vanishing result due to Micallef and Moore, which just looks at positive isotropic curvature, which is even slightly weaker than Brentley's result for the Ricci flow. And Micallef and Moore's theorem says if we are on a simply connected Riemannian manifold with positive isotropic curvature, then we have a homotopy sphere. Okay, so to check that our curvature conditions really are different, we should really compare it to positive isotropic curvature. And indeed, typically, so unless we're in small dimensions and we pick P in an unfortunate manner, our curvature condition lambda 1 plus and so on plus lambda n minus p positive is different from positive isotropic curvature. Namely, the two classes overlap, but neither class is contained in the other. And one can, for example, look at W-warp product metrics on spheres and produce metrics that satisfy the condition for the eigenvalues, but which don't have positive isotropic curvature. Great. So we really have a different curvature condition. The Ricci flow results, Micallef and Moore's theorem, and the theorem that we're discussing, they all describe different curvature conditions. There's one more result that I would like to mention. There's Gromov's bound on the Betti numbers. And well, the first observation is Gromov's result uses sectional curvature instead of the curvature operator. And there's the open question, what is the optimal bound in Gromov's theorem? And you may want to ask, can you show that the optimal bound is the torus using the Bochner technique? And you stumble upon the following observation. Well, if we look at the Bochner technique and we prove a result for a certain non-negativity condition, then once we go to the positivity condition, we get a vanishing result. But for manifolds with positive curvature, obviously we find manifolds with topology. So there's something fundamental which is different, which doesn't allow us to use sectional curvature here, which makes Gromov's theorem really remarkable again. And it's also useful to point out that Gromov's theorem obviously works for Betti numbers with arbitrary coefficients, whereas our theorem really looks at the de Rham cohomology. Great. So we've discussed the theorem. Let's get an idea for the proof. And the basic observation that we started with was we have to control the curvature term in the Bochner formula. And I've written it down here again. It's the sum lambda alpha times the norm of C alpha on omega squared. And then we said for Galois theorem, well, if all the lambda alphas are non-negative, then the curvature term is non-negative. That's the typical observation. Okay, but we can do slightly better. Why can we do this? Well, each individual piece, C alpha on omega, can't be very large. Okay, so more precisely, it's at most the minimum of p and n minus p times the norm of omega squared. Okay, that's the case because we've normalized the C alphas, otherwise we would have an extra norm here. Okay, so if we restrict ourselves again to up to half the dimension, then it's p times the norm of omega squared at most. Okay, so that's one observation that we need. Then we need the second observation. Well, what if all the lambda alphas are 0? What's the total sum? And we can actually compute the total sum as well. And the total sum is going to be huge in comparison. It's p times n minus p. Okay, so we've got plenty of terms, and each individual one is small. How can we prove these estimates? Well, the C alphas, they were skew-symmetric linear maps. Okay, and we can pick a normal form for those. And once we picked a normal form for the C alphas, we can grind it out. We've seen the previous result of Mikhailov and Wang for the Betti number of two forms with positive isotropic curvature. And again, we can identify a two form with a skew-symmetric map and use a normal form for the two form instead. If we do that, then we precisely we can start the same argument on this here and run into their theorem. But this shift to looking at the derivative of the representation, that allows us to look at the C alphas, use the normal form for those, and prove these estimates. Great. So what do we have? We've got a gigantic sum and small individual pieces. And each piece is weighted by an eigenvalue of the curvature operator. And now you can ask the question, well, how many eigenvalues can be negative so that you can still get to something positive at the end? Because you still have a lot of leftovers from this huge sum. And the answer is this. Let's pick kappa non-positive as before. So if we look at the average of the first n minus p eigenvalues of the curvature operator, then this argument shows that the curvature term in the Bochner formula is bounded from below by kappa p times n minus p norm omega squared. And that's all we need. Once we've got this lower bound on the curvature, constant times norm omega squared, then we can run the theory that was developed by Galois, and which relies on work of Peter Lee to get the estimation theorem by general techniques for the Bochner theorem. Great. And similarly, if kappa is 0, then we see that the curvature term is non-negative, and we can run the argument that we played at the beginning of this talk for one forms. Great. So that's the idea of the theorem and the new understanding of the derivative of the regular representation, how it interacts with P forms. Great. So we've discussed forms. And one of the advantages of the Bochner technique is that it also works for different types of tensors. Okay, so let's briefly talk about Lichner-Rovitch Laplacians. We're given a tensor T, a 0K tensor, an arbitrary tensor, and we can look at the Lichner-Rovitch Laplacian, which is given by the connection Laplacian. plus a constant times the Bochner Ricci of T, which is defined in the exact same way as we've seen it before for forms, this complicated expression involving the entire curvature tensor. And as before, we can actually write down the relevant curvature term in terms of the eigenvalues of the curvature operator times C alpha on T. Okay. And again, the entire technique works in the same way as before. If we have a harmonic tensor T, then we can look at the Laplace operator of the half the norm squared. It's going to be two pieces, the norm of the covariant derivative plus a curvature term. And so for P forms, we've seen this works incredibly well. And if we pick C is equal to 1 here, then we can look at the Hodge Laplacian, and a form is harmonic precisely if it's harmonic with respect to the Hodge Laplacian. The Bochner technique works well for other types of tensors too. We can look at symmetric two tensors, and the only modification that we really need is that we have to adjust the curvature term by a constant, namely by a half. But the case that we're really interested now for this talk is the case of algebraic curvature tensors. And in this case, we also need C as a half, but otherwise the general strategy is exactly the same. Great. So what happens for algebraic curvature tensors? So let's look at the curvature term in the Lichner-Horowitz Laplacian. We want to try and play the same argument again. So we want to bound each individual piece, and we want to calculate the entire sum. Okay, so if we have a 0k tensor, then we've got k components for vector fields to plug in. How big can each individual piece be? And the answer is it can be at most k squared times the norm of T times the norm of our skew-symmetric map. Okay, so the factor that we're interested in is this k squared. And for any tensor, k squared is going to be good enough. So let's remind ourselves, what did we see for forms? So now we've had the skew symmetry of the forms, and that implies that the square collapses to a linear factor. So if we have a P form, then we actually get P times norm omega squared. And technically this is for P up to half the dimension. If we're bigger than half the dimension, then we have n minus P again. Okay, so the symmetry really helped us to improve the estimate here. And this estimate is indeed optimal. Okay, so now we're interested in curvature tensors. And there are two things to observe. Okay, if we act with a skew-symmetric map on a curvature tensor, everything that is left is actually the trace-free part of the curvature tensor. So if we look at the part that corresponds or comes from the scalar curvature, metric Kulkani-Numatsu product with the metric itself, that naturally sits in the kernel of our action and vanishes. So the actually interesting tensor that we're looking at is the trace-free part of the curvature tensor. And indeed, the kernel of this is really given by those curvature tensors that have constant sectional curvature. So if CRM is 0 for all x's, then our tensor has to have constant sectional curvature. Okay, so the natural object to consider is really the trace-free part of the curvature tensor. It's a 0,4 tensor, so we would get 16 from 4 squared. But the symmetries of the curvature tensor, they say we gain a little bit of something, and we gain an 8 rather than a 16. So our estimate got a little better, and again, that's due to the symmetries of the tensor. So the estimate that we have really depends on the type of the tensor. Great. We know now how big each individual piece can be for an algebraic curvature tensor. And the second ingredient that we needed for forms, we wanted to know how big is the total sum. And we can compute the total sum. It's 4n minus 1 times the norm of the trace-free part of the curvature tensor minus 8 times the norm of the trace-free part of the Ricci tensor. All right, so what do we get from these two estimates? Let's see. Let's write this down on the next slide. So we've got the two estimates again. We've seen the 8, and we've got the norm of the trace-free part of the curvature tensor. Now, if our manifold is Einstein, then the second part here is just 0, and we can compare the norm of the trace-free part of the curvature tensor to itself. And the number that is important is 4 times n minus 1 divided by 8. That is n minus 1 over 2. And then the general Bochner technique that we've used before for forms also works for algebraic curvature tensors. And the result that we get is the following. So we're sitting on a closed Riemannian manifold. It's connected in Einstein. If we sum up the first n minus 1 over 2 eigenvalues, and this gives us a sum that is non-negative, then the curvature tensor has to be parallel. And moreover, if the sum over the first n minus 1 over 2 eigenvalues is positive, then actually we have to have constant sectional curvature. Constant sectional curvature because we've seen those tensors which sit in the kernel of this natural action, not quite an action, but that's a good way of thinking about it, that really consists of the curvature tensors with constant sectional curvature. Great. So that's the theorem for Einstein manifolds. And let's put this a little bit into context in the remaining minutes of this talk. So first of all, it generalizes a famous theorem of Tachibana. So Tachibana looked at non-negative curvature tensors, manifolds with non-negative curvature operator, really. And he proved that in this case, the curvature tensor is parallel. And if you have positive curvature operator, then the manifold has to have constant sectional curvature. Okay, and we generalize this to this sum of eigenvalues. And our condition, again, depends linearly on the dimension. And as for forms, we've seen Ricci flow results. And there's a Ricci flow version of this too, or at least the methods that Brenler uses come from techniques developed for the Ricci flow. If we have an Einstein manifold with non-negative isotropic curvature, again, then the curvature tensor is parallel and we sit on a locally symmetric space. And yeah, we notice that Einstein manifolds are stationary points of the Ricci flow. That's why Ricci flow techniques also imply theorems here. So these are the two main related results. I'd like to make one more comment on the Einstein condition. So we've seen that we need the Einstein condition to get the estimate on how many eigenvalues we can sum up. It's also important to get started entirely. So we've looked at the Bochner formula, and we need to have that the curvature tensor is harmonic. Okay. So if we have an Einstein manifold, then we can show that the curvature tensor is divergence-free, and that implies that we sit in the kernel of the Lichner-Rovitch Laplacian. And so namely, we've got a Bochner formula again, and we're using this half, and this is the equation that we need to get started in the first place. So the Einstein condition comes in multiple places in this theorem. It's not just for the eigenvalues. Great. So we've stated the theorem for dimensions bigger equal 5. What happens in dimension 4? Well, in dimension 4, if we plug in n equals 4, we get 3 over 2, which is 1.5. And then we have to take the floor function, and we get non-negative curvature operator. But we know with Ricci flow, we can do a little better. So in dimension n is equal to 4, we've got Bohm-Wilking's result that if we've got 2 positive curvature operator, then actually we're on a space form. And because Einstein manifolds are fixed points or stationary points of the Ricci flow, we see that we actually have to have constant sectional curvature right away. So in n equals 4, 2 positivity is sufficient. And the corresponding rigidity result was proven by Ni and Wu. So we also know in dimension 4, lambda 1 plus lambda 2 is sufficient to get parallel curvature tensor. So can we recover this theorem using the Bochner technique? Yes, we can, but we have to try a little harder. So in dimension n is 4, because we're sitting on an Einstein manifold, we can actually diagonalize the curvature operator in an Rx explicit way. And the basis is essentially given by the basis for the curvature tensor of CP2. Okay, once we have that, we can compute the exact curvature term in the Bochner formula and write it out explicitly. And we can use that the Bochner reach and the curvature tensor that we use really come from the same manifold. And that's what helps us to gain a little bit. And we can also show that lambda 1 plus lambda 2 is sufficient for n is equal to 4. Okay, so the general method that we used earlier was if the curvature operator satisfies lambda 1 plus lambda n minus 1 over 2 is non-negative, then the expression in the Bochner formula, the curvature term is non-negative for whatever curvature tensor we plug in. And here we can really use that we use the curvature tensor of the Riemannian manifold and the Bochner reach of the same Riemannian manifold. Great. And to conclude, I'd like to remark that there's a similar theorem for Weyl tensors, so a subclass of algebraic curvature tensors or curvature tensors on a manifold. What do we need? Again, we need the Bochner formula. So we've seen for an Einstein manifold, we had to have, Einstein implies divergence-free curvature tensor. So now for Weyl tensors, we assume that the Weyl tensor is divergence-free. Once we have that, we can write the Bochner formula down again, and we get the analogous condition lambda 1 plus up to lambda n minus 1 over 2 positive. Then the Weyl curvature vanishes and our manifold is conformally flat. We can also prove the corresponding rigidity result that the Weyl tensor is parallel if lambda 1 up to lambda n minus 1 over 2 is non-negative. And I think this is a good place to stop. Thank you very much.
Thank you for a beautiful talk. Are there questions? Feel free to unmute yourself if you have a question.
So in the last result, you actually see that the metric you are given is conformally equivalent to a flat metric. Is that right?
Well, you sit on a manifold which is conformally flat. Yes, the Weyl tensor vanishes of this manifold. So if the Weyl tensor is divergence free to start, and you have this curvature condition, then actually the Weyl tensor is 0, and you are already conformally flat. Yeah.
Are there other questions? Okay, well, let's thank the speaker again. And our next talk is on July 1st. It'll be Yuri Nikolaevsky, and the time will be 11 p.m. Universal Time. So thank you, everyone.
Thanks.
Bye-bye.